Introduction.
Good morning, teacher.
Good morning, students. Today we will learn chemical reactions of aldehydes and ketones and carboxylic acids.
Teacher, what are carboxylic acids?
Carboxylic acids are the organic compounds which contain carboxyl group. Now, who will tell me what is carboxyl group?
Carboxyl group consists of carbonyl group and hydroxyl group.
Very good, Ramesh. In this lesson, we will learn more about carboxylic acids. Objectives. At the end of this lesson, you will be able to describe chemical reactions of aldehydes and ketones, explain uses of aldehydes and ketones, describe nomenclature and structure of carboxyl group, give methods of preparation of carboxylic acids, give a brief on physical properties of carboxylic acids, describe chemical reactions of carboxylic acids, mention uses of carboxylic acids. Chemical reactions. Nucleophilic addition reactions. Mechanism of nucleophilic addition reactions. Those addition reactions which are initiated by nucleophile are called nucleophilic addition reactions. In this reaction, a nucleophile attacks electrophilic sp2 hybridized carbon. The hybridization changes to sp3 and a tetrahedral alkoxide intermediate is formed, which reacts with proton to form addition product. Reactivity. Steric and electronic factors cause aldehydes to be more reactive than ketones towards nucleophilic attack. Sterically, a ketone has two alkyl or aryl groups attached to a carbonyl carbon atom, whereas an aldehyde has hydrogen atom and one alkyl or aryl group on the carbonyl carbon. Thus, addition to a ketone will result in relatively more crowding in the transition state, leading to product and therefore a slower rate of reaction. Electronically, the carbonyl carbon atom of an aldehyde carries only one electron donating alkyl group, whereas that of a ketone has two. Thus, the aldehyde carbonyl carbon atom is relatively more electron poor and has a greater tendency to attract a nucleophile. Chemical reactions. Some important examples of nucleophilic addition and nucleophilic addition elimination reactions. Addition of hydrogen cyanide. The reaction occurs slowly with poor HCN and is therefore catalyzed by a base. The generated cyanide ion is a stronger nucleophile and it adds to the carbonyl group of aldehydes and ketones to form compounds called cyanohydrins. Addition of sodium hydrogen sulfite. On treating aldehydes and ketones with concentrated solution of sodium hydrogen sulfite, they form bisulfite addition products. Chemical reactions. Addition of alcohols. Aldehydes react with alcohols in the presence of dry hydrogen chloride. A hemiacetal is first formed, which reacts with another molecule of alcohol to form a stable acetal. Ketones do not react with alcohols directly, but kettles can be prepared by alternate methods. Ketone reacts with ethylene glycol in the presence of hydrochloric gas and form ethylene glycol kettle along with water. Chemical reactions. Addition of ammonia and its derivatives. Ammonia and its derivatives react with carbonyl compounds in acidic medium to give addition products, which undergo elimination of water molecule to give the final product as imine derivatives. Z can be alkyl, aryl, OH, NH2, C6H5NH, NHCON, H2, etc. Chemical reactions. Reduction. Reduction to hydrocarbons. Aldehydes and ketones can be reduced to hydrocarbons by the action of amalgamated zinc and concentrated hydrochloric acid, that is known as Clemmensen reduction. Wolff-Kishner reduction. Aldehydes and ketones can be reduced to hydrocarbons by the action of hydrazine and potassium hydroxide at elevated temperature. Chemical reactions. Oxidation. Aldehydes are easily oxidized to carboxylic acids containing same number of carbon atoms as the parent aldehyde. Aldehydes are easily oxidized because of the presence of hydrogen atom on the carbonyl group, which gets converted to OH group without cleavage of any bond. Hence, aldehydes are not only oxidized by strong oxidizing agents like potassium permanganate and potassium dichromate, but can be oxidized even by mild oxidizing agents like Ag2+ and Cu2+ ions under basic conditions. The oxidation of ketones occurs under drastic conditions and requires strong oxidizing agents like acidified potassium dichromate solution or alkaline potassium permanganate solution. The oxidation of ketones results in the formation of carboxylic acid with lesser number of carbon atoms. Chemical reactions. Tollens test. Propanol, being an aldehyde, reduces ammoniacal silver nitrate solution, that is Tollens reagent, to silver mirror, but propanone, being a ketone, does not. Felling's test. Felling solution is a mixture of aqueous copper sulfate Felling A and alkaline solution of Rochel's salt, that is sodium potassium tetarate Felling B. These two solutions are mixed and then pour some aldehyde solution into the Felling's reagent, and then upon heating it forms a reddish brown precipitate. Oxidation of methyl ketones by haloform reaction. Methyl ketones undergo oxidation with sodium hypohalide solution, that is sodium hydroxide and halogen. The reaction produces haloform and sodium salt of carboxylic acid. This reaction is known as haloform reaction. Chemical reactions. Reactions due to alpha hydrogen. Acidity of alpha hydrogens of aldehydes and ketones. The alpha hydrogen atom in aldehydes and ketones is acidic. This is due to the strong electron withdrawing effect of the carbonyl group and resonance stabilization of the conjugate base. Acidity of alpha hydrogens in aldehydes and ketones is due to strong electron withdrawing effect of the carbonyl group and resonance stabilization of resulting anion. Aldol condensation. It is dimerization of an aldehyde or ketone having at least one alpha hydrogen in the presence of dilute alkali such as dilute sodium hydroxide, sodium carbonate, etc., catalyst to a hydroxyaldehyde or ketone called aldol. Ethanol, in the presence of dilute sodium hydroxide, undergoes condensation to form a syrup liquid known as aldol. On heating, aldols eliminate water to form unsaturated compounds. Propanone, in the presence of barium hydroxide, gives ketol. On heating, ketols eliminate water to form unsaturated compounds. Chemical reactions. Cross-aldol condensation. Aldol condensation between two different aldehydes or ketones is known as cross-aldol condensation. A mixture of ethanol and propanol when heated with dilute sodium hydroxide solution gives 4 different products. Chemical reactions. Other reactions. Cannizzaro reaction. In the presence of concentrated alkali, aldehydes containing no alpha hydrogens undergo self-oxidation and reduction to yield a mixture of an alcohol and a salt of a carboxylic acid. This reaction is known as the Cannizzaro reaction. Formaldehyde reacts with concentrated potassium hydroxide to form methanol and potassium formate. Benzaldehyde reacts with concentrated sodium hydroxide to form benzyl alcohol and sodium benzoate. Electrophilic substitution reaction. In benzaldehyde, aldehydic group is ring deactivating meta-directing group, so the rate of electrophilic substitution will be slower than that of benzene. Benzaldehyde reacts with chlorine and ferric chloride solution and it forms metachlorobenzaldehyde and hydrochloric acid. Uses of aldehydes and ketones. A 40% aqueous solution of formaldehyde is known as formalin and is used to preserve biological specimens and to prepare bakelite. Acetaldehydes are used as a starting material in the manufacture of acetic acid, ethyl acetate, vinyl acetate, polymers, and drugs. Benzaldehyde is used in perfumery and in dye industries. Acetone and ethyl methyl ketone are common industrial solvents. Carboxylic acids. Organic compounds containing carboxylic group are called carboxylic acids. The carboxyl group is made up of carbonyl and hydroxyl group, hence its name is carboxyl group. Carboxylic acids may be aliphatic or aromatic depending upon whether carboxyl group is attached to aliphatic alkyl chain or aryl groups respectively. Nomenclature and structure of carboxyl group. Nomenclature. The common names end with suffix I, C, acid. The common names are derived from the Latin or Greek names of their source. For example, the name formic acid comes from the Latin word formica, which means ants, as formic acid was first obtained by distillation of red ants. Acetic acid derives its name from acetum, which means vinegar, and butyric acid has its name from butyrum, meaning butter. In IUPAC nomenclature, the IUPAC name of the aliphatic carboxylic acids is obtained by replacing terminal E from the name of the corresponding parent alkane by O, I, C, followed by the word acid. The substituted and branched chain acids are named as derivatives of the longest chain acid. The positions of the substituents are indicated by Arabic numerals, with carbon of the carboxyl group being number 1. In naming acids containing more than one carboxyl group, the final E in the name of the parent alkane is retained and the number of carboxyl groups are indicated by adding the multiplicative prefix di, tri, tetra, etc. to the term OIC. Examples: 4-hydroxybutanoic acid, prop-2-enoic acid, propane-dioic acid. Aromatic acids. The simplest aromatic monocarboxylic acid, C6H5COOH, is named as benzoic acid. The IUPAC names of the substituted acids are derived from benzoic acid. Nomenclature and structure of carboxyl group. Structure of carboxyl group. The functional group of a carboxylic acid is the carboxyl group. The carboxyl carbons show the resonance structures as given below. Methods of preparation of carboxylic acids. From primary alcohols and aldehydes. Primary alcohols and aldehydes get oxidized to corresponding carboxylic acids with oxidizing agents like chromium trioxide in acidic media. 1-decanol reacts with chromium trioxide in acidic medium and forms decanoic acid. From alkyl benzenes. Aromatic acids can be prepared by oxidation of alkyl benzenes with alkaline permanganate. Toluene reacts with potassium permanganate in alkaline medium and forms benzoic acid with some water. From nitriles and amides. Nitriles are also called as cyanides. On hydrolysis of cyanides in presence of an acid or alkali yield carboxylic acid. Hydrolysis of acetonitrile in presence of an acid, it forms ethanoic acid. On hydrolysis of propanamide in the presence of an acid, it forms propanoic acid and ammonium ion.
Methods of preparation of carboxylic acids. From Grignard reagents. Grignard reagents, when treated with carbon dioxide in the presence of dry ether, forms salts of carboxylic acids, which in turn gives carboxylic acids after acidification. Methyl magnesium bromide reacts with carbon dioxide in the presence of dry ether. It forms salt of carboxylic acid, which forms ethanoic acid and hydroxy magnesium bromide after acidification. From acyl halides and anhydrides. The hydrolysis of acid chlorides produces carboxylic acids. On hydrolysis of acetyl chlorides, it produces acetic acid. The hydrolysis of acetic anhydride produces acetic acid. From esters. Acidic hydrolysis of methyl benzoate gives benzoic acid and methanol. Physical properties. The first 9 aliphatic carboxylic acids are colorless liquids with pungent smell, while the higher members are colorless, odorless, waxy solids. Benzoic acid is a crystalline solid. Carboxylic acids have quite high boiling points due to the presence of intermolecular hydrogen bonding, which results in the formation of dimeric structures. The first 4 aliphatic members are soluble in water due to intermolecular hydrogen bonding with water molecules. With increasing size of the alkyl group, the non-polar part of the molecule predominates, thereby reducing the solubility in water. The higher members are practically insoluble in water. Chemical reactions. Reactions involving cleavage of OH bond. Acidity. Reactions with metals and alkalis. Carboxylic acids are one of the most acidic organic compounds. They react with sodium metal to liberate hydrogen gas. Sodium metal reacts with ethanoic acid and gives sodium acetate and liberates hydrogen gas. Benzoic acid reacts with bases to form salt and water. Ethanoic acid reacts with carbonates to liberate carbon dioxide gas. Chemical reactions. Carboxylic acids are stronger acids than phenols. In carboxylate ion, the negative charge is equally distributed over 2 electronegative atoms that are oxygen atoms, while in phenoxide ion it is present only on one oxygen. Thus, carboxylate ion is more stabilized as compared to phenoxide ion. Hence, carboxylic acids ionize to a greater extent than phenols, furnishing higher concentration of hydrogen ions. Therefore, carboxylic acids behave as stronger acids than phenols. Effect of substituents on the acidity of carboxylic acids. The electron withdrawing groups stabilize the carboxylate ion by dispersal of the negative charge and increase the strength of the acid. On the other hand, the electron donating groups cause concentration of negative charge, destabilize the carboxylate anion, and hence decrease the strength of the acid. Electron withdrawing groups such as halo group NO2, CN, etc. increase the acidity of carboxylic acids, whereas electron donating groups like alkyl groups decrease the acidity of carboxylic acids. The effect of number of the substituents is illustrated by the chloro-substituted acetic acids. The acid strength increases from chloroacetic acid to trichloroacetic acid. Chemical reactions. Reactions involving cleavage of COH bond. Formation of anhydride. Carboxylic acids on treatment with phosphorus pentoxide form anhydrides by elimination of a water molecule from two molecules of the carboxylic acid. Esterification. Carboxylic acids react with alcohols in the presence of concentrated sulfuric acid to form esters. Chemical reactions. Reactions with phosphorus pentachloride, phosphorus trichloride, and thionyl chloride. Carboxylic acids react with phosphorus pentachloride, phosphorus trichloride, and thionyl chloride to form acid chlorides. Carboxylic acid reacts with phosphorus pentachloride to form acid chlorides, phosphoryl chloride, and hydrochloric acid. Carboxylic acid reacts with phosphorus trichloride to form acid chlorides and phosphorus acid. Carboxylic acid reacts with thionyl chloride to form acid chlorides, sulfur dioxide, and hydrochloric acid. Reaction with ammonia. Carboxylic acids react with ammonia to form ammonium salt on heating at elevated temperature, that is greater than 100 degrees Celsius. Chemical reactions. Reactions involving carboxylic group. Reduction. Carboxylic acids can be easily reduced to primary alcohols by lithium aluminium hydride in excellent yield. Decarboxylation. Sodium salts of acids when heated with soda lime, alkanes are formed. When sodium acetate is heated with sodium hydroxide and calcium oxide, it forms methane and sodium carbonate. Chemical reactions. Substitution reactions in the hydrocarbon part. Halogenation. The reaction takes place between aliphatic carboxylic acid and chlorine or bromine in the presence of red phosphorus. It involves the substitution of chloro or bromo group at the alpha carbon atom of carboxylic acids. The reaction is known as Hell-Volhard-Zennelsky reaction. Ring substitution. Aromatic carboxylic acids undergo electrophilic substitution reactions. The carboxyl group, being deactivating, is meta-directing. On adding concentrated nitric and sulfuric acid into benzoic acid, it is converted into meta-nitrobenzoic acid. On adding bromine and ferric bromide into benzoic acid, it is converted into meta-bromobenzoic acid. Uses of carboxylic acids. Acetic acid is widely used as a food preservative and condiment. Acetic acid reacts with other chemicals to form numerous compounds of commercial importance. They include cellulose acetate, which is used in making acetate rayon, non-flammable motion picture film, lacquers, and plastics. Benzoic acid is used regularly in food preservation, in treatment of bacterial infections, and combined with other chemicals to create products like repellents and perfumes. Did you know? Vinegar is typically a 4 to 8% solution of acetic acid. The rest is water and trace amounts of other molecules. The acetic acid in vinegar is formed by the fermentation of ethanol. One of the most effective ways to wash fruits and vegetables is with dilute vinegar. Summary. Let us summarize what we have learnt. The addition reactions which are initiated by nucleophile are called nucleophilic addition reactions. Steric and electronic factors cause aldehydes to be more reactive than ketones towards nucleophilic attack. Aldehydes can be easily oxidized to carboxylic acids. Aldehyde reduces ammoniacal silver nitrate solution, that is Tollens reagent, to silver mirror. Felling solution is a mixture of aqueous copper sulfate and alkaline solution of Rochelle's salt, that is sodium-potassium tetarate. The alpha hydrogen atom in aldehydes and ketones is acidic. This is due to the strong electron withdrawing effect of the carbonyl group and resonance stabilization of the conjugate base. Aldol condensation is dimerization of an aldehyde having at least one alpha hydrogen in presence of dilute alkali such as dilute sodium hydroxide, sodium carbonate, etc., catalyst to a hydroxyaldehyde called aldol. Aldol condensation between two different aldehydes or ketones is known as cross-aldol condensation. Organic compounds containing carboxyl group are called carboxylic acids, and the carboxyl carbon show the resonance structures. Carboxylic acids have quite high boiling points due to the presence of intermolecular hydrogen bonding, which results in the formation of dimeric structures. Acetic acid is widely used as a food preservative and condiment, and it also produces numerous compounds of commercial importance by reacting with other chemicals.